Okay guys, this is some info for 3.3. I'm probably going to do a couple parts to this. So first thing is to learn about our basic functions. So the idea here is going to be that we want to know the shapes of a lot of different graphs. And to give us some flexibility, we're going to have some basic shapes that we know, and then we're going to talk about over the next few days making small changes to the equations and figuring out what that will do to the graph. So we're going to start with 6 basic functions. And I'll put the equations down here for you and talk about some of the things we're going to be looking at, and then we'll go through the graphs. So our basic functions are going to be x squared, this one we should already be familiar with, x cubed, which generally quite a few people have seen as well, the square root of x, absolute value of x, and then we're going to do a couple that might be a little weird at first, but we'll be happy we know about them at the end of the quarter. So f of x equals 1 over x, and f of x equals 1 over x squared. This first one, f of x equals 1 over x, is often called the reciprocal function because that's what it does. Whatever input you give it, it gives back the reciprocal. Okay, so these are going to be our basic functions, and by the end of watching this video and working on this, you want to know by heart exactly what the graph looks like as soon as you see the equation. So immediately when I see absolute value of x, I should have a picture in my head of what that function looks like, and then if I need to, I can talk about specific points that are on the graph and other characteristics. Okay, let's also put down here some of the things we're going to be looking for. So one, we just want to know about general shape. So every single one of these, that's what should automatically pop into our head when we see the equation, is what the general shape of the graph is. We also want to be able to look at specific points, so we'll do this for each graph. The idea is you have an equation, so you should be able to find as many points as you need. We want to be able to spot the domain and the range of any one of these functions. We would like to be able to say when and where the functions are increasing or decreasing. And we want to be able to talk about symmetry. So before we jump into the graphs, let's just say a little bit more about the symmetry stuff, and then I think we're ready for them. Okay, so there are a couple of particular sorts of symmetry that we'll look at, and then there'll be some more general ones that come up along the way as well. So for symmetry, some really common types of symmetry that we'll see are even functions. So this can be our first one. So an even function is symmetric about the y-axis. So if you look at the y-axis as splitting the graph into 2 halves, the 2 halves should be mirror images. So again, symmetric about the y-axis. Okay, so number 2 of our common symmetries that we'll see is odd. We'll also look at odd functions. An odd function is symmetric through the origin This one is a little bit trickier at first, but once you get the idea of what the picture looks like, it's fairly easy to spot. We'll be looking for what's in quadrant 1 to be reflected across both the x and y axis and match up with what's in quadrant 3 or vice versa, and the same thing if there's something in quadrant 2, if we reflect it across the x and y axis, it should match up with what's in quadrant 4. So those are some common ones. One that's not quite so common, but it'll be interesting to us later on, and it does show up on one of our basic functions, is, it doesn't have a special name, but just symmetric about y equals x. So there's sort of an interesting diagonal symmetry that sometimes shows up on graphs, and we particularly want to point it out now because it's going to be really interesting when we're talking about inverse functions. Okay, so let's get going and actually look at these 6 graphs, and then I'm going to take a minute at the end to also show you some similar graphs on your calculator that I just want you to have sort of a general idea about for later on in the quarter. Okay, so I actually have these printed up so you get the nice clean version. This is x squared. So this is going to be our basic quadratic functions, and we're already supposed to have a pretty good background in quadratics, so we should be familiar with this. So it's a parabola, opens up, the vertex is right at the origin. This is a particularly nice point to pay attention to, 0, 0. The vertex is a really key characteristic of this graph, so when we start moving the graph around and making changes to it, that's going to be a point that we want to pay attention to. So I labeled a point for you just kind of looking at this graph, but again, the idea is you should be able to label as many points as you want to because you have an equation here. So if we want more points, we can just plug in any x value we want or y value and use the equation f of x equals x squared or y equals x squared to find more points. So for example, if I plug in 1 for x, I can see it on my graph because I have this nice grid, but I can also see it from the equation. 1 squared is 1, so the graph should go through 1, 1. And if I plug in 2 for x, 2 squared is 4, so when x is 2, y is 4. And similarly on the other side, if I plug in -1, -1 squared is 1, so it goes through -1, 1. Let's jump all the way to -3. -3 squared is 9, so there's a point way up here, -3, 9. And we could do this all day long, as much as we want to. In fact, a really nice thing to be able to do is to label an arbitrary point on this graph. So I'm just going to call this x-coordinate A, and it could be anywhere. It looks like mine is maybe around 2.6, but that doesn't even matter. The idea is that no matter where I drew this point, if it was on the graph, I should be able to give the general idea. So if we look back here, I plugged in an x-coordinate, and in order to get my y-coordinate, I had to square it. So the relation here is that whatever the x-coordinate is, the y-coordinate is the square of that. So if our x-coordinate is A, our y-coordinate will be A squared. So that's a general point on this graph. Okay, other things we wanted to talk about. I won't mention all of these for all the graphs. Notice here the domain is all real numbers. We can get that from the graph or the equation. This graph heads off forever both directions. So no matter how far out we go this way, if we go up far enough, we're going to be able to find a y value on the graph. So that's domain of all real numbers. We can also look at the equation and say, okay, we're squaring to get a y value. We could square anything we want. There's nothing that's going to give us domain problems when we're trying to square. The range is a little more interesting. Here range is strictly y greater than or equal to 0. We don't get any negative y values, so y is greater than or equal to 0. This function shows some increasing and some decreasing. I haven't given you an official definition, but just kind of in the sense of the word, we want to look at things headed from left to right. So as our x values increase, what happened to our y values? And notice on the left-hand side, our function, our y values are decreasing. So the graph decreases from -infinity and right up until I get to 0. And then on the other side of the y-axis, the y values are increasing. So this is increasing function from 0 to positive infinity. So when I'm describing that -infinity to 0 and then 0 to positive infinity, I'm describing in terms of x values. And that's important because this is a function. So if I describe in terms of x values, there's no chance that I'm being ambiguous. If I describe in terms of y values going from 0 to infinity, that could actually be either side of the graph. So x values are going to be a good way to describe everything except for range. Last thing I think I want to point out on this one is symmetry. This actually does show some symmetry. This is a mirror image across the y-axis, so this is an even function. So this first one we look at is even. So mirror image across the y-axis is even symmetry. Okay, so number 1 down. Number 2, this is x cubed, And we could do the same thing. You can plug in any x value you want to get out y values. I didn't make my graph real big, so we can see some nice points with integer coordinates. There's 1, 1. It looks like it stops right up here at 2, 8. 0, 0 is a nice point again on this graph. That's the place where this graph changes bend. So this is called concave down, where the bend is headed downward. And this is called concave up, where the bend is pointed upward. And that switch happens right at 0, 0. So the important thing there is just to realize that that's kind of a key point on your graph. And again, on this side, looking for some nice integer coordinates, it will hit -1, 1 and -2, -8. I think I said that last one wrong, -1, -1. Anything you want, you can plug in here and you can cube it. So it's easy when we move on to doing transformations, which is our next topic, to use points that have integer coordinates, but there's certainly infinitely many points on here that don't have nice integer coordinates, and there's nothing wrong with them. So just like on the last graph, we can come in here and we can say, okay, well, what if I wanted to label an arbitrary point? So that has an x value of a. In this case, our y value will be a cubed. This function is always increasing, kind of interesting. We have a little flat spot right here, but otherwise increasing y values and then more increasing y values. Other thing on this one is, once again, we have some interesting symmetry. This is a great example of an odd function. So remember, odd was symmetric through the origin. So what I'm noticing here is that what I have in quadrant 1 looks a lot like what I have in quadrant 3. And that's kind of what I'm hoping to see. So the idea would be if you pick up 1/4 of the graph, so I'm just going to pick up quadrant 1, and you flip it across the y-axis and then across the x-axis. In order doesn't actually matter there, so you could also do the opposite. You should line right back up with the other part of your graph, and we do. So if we pick this piece up and flipped across, and then flipped across again, it would match right up with the segment in quadrant 3, so that's an odd function. Okay, next graph. Next one it looks like I have set up is the absolute value of x. So we should be familiar with kind of the basic idea of what absolute value does. It takes any input and it basically eliminates the sign. So if you plug in a positive number, it does nothing. If you plug in 0, it does nothing. If you plug in a negative number, it will change the sign, so it's a positive number, and give you that back. So what you see over here is on this side, it's actually exactly y equals x, because when you plug in a positive number, you just get back exactly what you started with, which is what y equals x does. On this side, we have y equals -x, because here we plug in a negative number and it gives us the opposite sign. There's the negative x part to get the y value. So again, 0, 0, really kind of an important point on this graph when we're going to do transformations, because that's where the corner is. And we can get tons more. The idea is on this side, the x-coordinate and the y-coordinate are the same, so 2, 2 is a good point. On the other side, the x-coordinate and the y-coordinate are opposite, so -3, 3 would be a point, and there's tons of others. Symmetry, this one does show symmetry again. This is another example of an even function. You can see the symmetry across the y-axis, this mirror image, so that is our even function. This one does have infinite domain. It's going from -infinity all the way to +infinity. The range, however, does have a restriction on it. Range, once again, like with x squared, is y greater than or equal to 0. Okay, getting there halfway through. This is y equals the square root of x. Notice that it sort of looks like half of a parabola turned on its side, and it actually is that. It's not just coincidence. That's exactly the shape that we're getting here. So here, 0, 0, once again, for tons of our basic functions that we're going to look at, 0, 0 is an important point. Here it's important because that's where the graph actually ends. If we try and plug in anything less than 0, we're going to have domain problems with that square root. So 0, 0 is the endpoint of this graph. And then to get points with nice integer coordinates, we want to be plugging in x values that are perfect squares. So 1 is a perfect square, and its square root is 1. That will be a point. The next perfect square is 4. Its square root is 2. The next one we'll hit is 9. Its square root is 3, and we could keep going 16, 4, 25, 5. And again, there's infinitely many points in between that are perfectly good. They just don't have integer coordinates, which can make life a little easier with transformations, but don't be put off by those other points. If we want to be a little more general and say this is the point with the x coordinate a, the rule for its y coordinate is that it would always be the square root of a. So this is our square root graph. So as I mentioned, this one actually does have domain restriction. This is the first one we've seen with the domain restriction. Here x has to be greater than or equal to 0, and y is also greater than or equal to 0. This is the first one that we see that does not show any symmetry at all, so no symmetry showing up here. And this one is another one that's always increasing. Everywhere on its domain, it has increasing y values, nowhere where that switches direction. Okay, 2 more. So these two are a little bit messy and strange at first, but we're going to be really glad we're comfortable with them later on. So this first one is the reciprocal function, f of x equals 1 over x. And I don't know if you can see this, but it has 2 branches, one up here in quadrant 1, one down here in quadrant 3. And then I've drawn in some dashed lines here along the x-axis and the y-axis. The idea is that this is the first function that we get to look at that shows asymptotic behavior. So the thing that's going on right here near the y-axis is that the y values are skyrocketing, and we don't actually ever hit the y-axis. So here we're seeing this behavior where our graph increases and gets closer and closer, infinitely close to the y-axis, and its behavior tends to be a lot like the y-axis. So it's getting really close to just being that vertical line at the y-axis. Similarly, we have a horizontal asymptote. So this one was vertical asymptote. Horizontal asymptote is similar, not exactly the same idea. We generally get a vertical asymptote when our function is undefined. So here when x is 0, this is undefined, and plugging in values really, really close to 0 gives us the reciprocal of a tiny little number, which becomes a really, really big number. Horizontal asymptotes are generally all about global behavior. So this is thinking about if I plug in a really, really big x value, what is my graph going to act like? So when I start plugging in huge values here, 1,000,000 or 1,000,000,000 or 1,000,000,000,000, whatever, what I'm going to see is this fraction is going to get really, really small. So if I plug in very big positive numbers, the reciprocal is going to be a very small positive number. This will continue to get closer and closer to the x-axis. If I plug in really big negative x values, I'm going to get really small negative y values, so closer and closer to the x-axis. This graph doesn't happen to cross either asymptote ever, but just something to try to remember for later on. Well, we wouldn't cross this vertical asymptote. That's a spot where the function is undefined. It is completely legal to cross horizontal asymptotes. They're only telling us about global behavior, so what happens when x is really big. So we will see graphs later on that sometimes cross and come back up or do all sorts of interesting things, and that's nothing we're worried about. So for this graph, when we start moving into doing transformations, those asymptotes are going to be really important to follow. So this one's at y equals 0, and the vertical is at x equals 0, and we want to keep track of those and relabel them if they ever get moved around. Otherwise, plugging in points, 1's a really nice point to plug in because the reciprocal of 1 is just 1. We could also try plugging in, say, 3. The reciprocal of 3 is 1/3. Or we could plug in 1/2. The reciprocal of 1/2 is 2. So we get all these points, and we should have corresponding points because we do see some symmetry here again in quadrant 3. So if I plug in -1, its reciprocal is -1. If I plug in -3, its reciprocal is -1/3. If I plug in -1/2, its reciprocal is -2, and so on. So again, we are seeing our symmetry here in these points. And the symmetry, the big one that I hope we see right away, is that this is symmetric through the origin. Again, this is another odd function. So if I pick up the stuff in quadrant 1 and I reflect it across the y-axis and then across the x-axis, it would line right up with what's in quadrant 3. So that is an odd function. This one has that other sort of strange symmetry that I mentioned would be important to us later. This is also symmetric about y equals x. So if you think about y equals x, I'm going to draw it in here. looks something like this. This is something you can start trying to train your brain to spot right away. If I pick this up and do a diagonal flip, pick up everything above y equals x, it would line right up with everything below y equals x. That's what I'm talking about with symmetry about y equals x. And I promise we'll talk about why we care about that one later on, but for now, just see if you can kind of see that going on, spot that going on. Okay, last one is similar. 1 over x squared is the very last one. My computer did a little bit of a funny job. This looks like it has kind of a corner here. It doesn't. It should be a nice smooth graph, so sort of ignore that. This should come through with a nice little curve here, no weird corners at all. So in quadrant 1, it looks fairly similar to 1 over x. It's not exactly the same, but it's close. It still hits 1, 1. The other points will be changed a little because of squaring that x coordinate before you take its reciprocal. So here, for example, if I plug in 3, the reciprocal of 3 squared is 1/9, so it is going to change a little, but still very similar. And again, you can get as many points as you want by plugging into that equation. This will have the same sort of asymptotic behavior. It does have a vertical asymptote along the y-axis at x equals 0, and a horizontal asymptote along the x-axis at y equals 0. Because of the square, the big difference is going to be that instead of having some negative y values when we plug in negative x values, we'll still have positive y values. So this side ends up also above the axis. So here our range, we can say both. Our domain is that x can't be 0. Anything else is fine here. But our range is all y values greater than or equal to 0. So no negative y values here. In fact, not even equal to. Just strictly greater than 0. We don't hit that x-axis. Okay, so that is your complete list. And again, your number one job is to commit those basic shapes to memory. As soon as you see any one of those equations, you should have a picture of a graph in your head. You shouldn't have to work at it. We can go and fill in the details later, but you should have that basic picture down right away. So I think the only other thing I want to show you really quick in this one is, I'm just going to go ahead and show you on the calculator. There's some similarity. This might be a little questionable, but I'm going to try and move this down so it's zoomed in a little bit more. Sorry for the glare. This was definitely questionable. Okay, if I haven't made you all nauseous, we are going to try and move out of that glare. There we go. Okay, hopefully this is visible. I'm going to plug in x squared and x to the 4th and x to the 6th, and I think that'll get us the idea. In fact, I'm going to turn these two off and then I'll go back in and turn them on one at a time. So I'm just going to go zoom, I don't know, standard will probably do it. So zoom 6 on this one. This is the 89, so if it looks just a little bit different, let's see if we can get this to not wobble. If it looks just a little bit different than yours, that might be why. So this is looking slightly blurry on my end, but there's the basic shape. We already know it. It's a parabola. What I want you to see is, back into my y equals, what happens if I turn on the other two. So into my graph. Okay, so there's x squared. There's x to the 4th. Ooh, and you can barely see a difference probably on your end. There is x to the 6th. What I want you to see here is that they're all sort of similar shapes. As I increase that power, it gets a little steeper in here in the middle, and it's kind of hard to see, but it actually flattens out a little bit on the bottom. So let me see if I can zoom in. Okay, so there's x squared when I zoom in. There, I think you can see it a little bit. X to the 4th is actually a little bit lower down, closer to the axis, right near the origin, and x to the 6th is even a little bit lower. Okay, so I apologize because I know this is being blurry and wobbly, but I want to show you just the same thing with the odd functions. So I'm going to look at x cubed, x to the 5th, x to the 7th. I'm going to try that again even because it didn't work. X cubed, x to the 5th, x to the 7th. Wow. X cubed, x to the 5th, there we go, x to the 7th. Okay, x to the 7th. There we go. Third time. Okay, so that's what I have plugged in there. Can't tell if that's going to be legible or not for you guys. So I'm going to go back to Zoom Standard. So there's x cubed, and there's x to the 5th, and there really close is x to the 7th. So again, what you should see is as the power gets bigger, it gets a little steeper in here, but the basic shape is pretty close to x cubed. And then same thing if we zoom in right near the origin, there's x cubed, x to the 5th, it's even harder to see here, x to the 7th. Let me zoom in once more and see if that's a little bit more visible. So there's x cubed. This looks terrible. Let's try -1 to 1, -1 to 1. Okay, x cubed, x to the 5th, and x to the 7th. So this is really close to the origin. Notice that x cubed actually gives you the bigger y values when you're close to the origin, and x to the 5th and x to the 7th get smaller from there. Okay, I'm going to let you go on this because I'm probably making you all seasick by this wobbly calculator part. I'll post another chunk with some info about piecewise functions.